For this video, we're going to be talking about nutrient cycling. Basically, how do nutrients move through the environment and what patterns between the atmosphere, biosphere, geosphere do they tend to follow? So, when we're talking about how nutrients move around the environment, it's going to depend on each different nutrient. And some of them will have an atmospheric component, some of them won't. Where they're found, are they found in the rocks or not? Are they produced by organisms? And each one has a little bit of a story. So we're going to start off simple here with the water cycle. The water cycle most people are very familiar with, right? You have water on the ground, it's going to evaporate up into the atmosphere, and it's going to precipitate out as rain or snow or ice, right? So it's going to fall down from the sky. Now, it can go through different things there. One, it can run off, so it can stay above ground and move above ground. But a lot of it actually ends up infiltrating into the ground and moving through the ground as groundwater. Now, when people hear groundwater, they often think like a big lake under there. That's not the way it is. It's actually in between the particles of the whatever the geology or the soil is that's there. So it'll infiltrate into the ground and then it'll move through there. Now it can also seep out from the ground into the surface water again or surface again, or just move through it as a whole. Once it's above ground, it can then evaporate. And so the water cycle kind of moves through this evaporation, move to the atmosphere, precipitation, move above or below ground until it comes back up, and then evaporate again. Now, the carbon cycle has a lot to do with carbon dioxide. So, where is carbon dioxide? When is it being taken in, and when is it being expelled? Now, carbon dioxide has a lot of biotic and abiotic components to it. Now, if we talk about the biotic piece, plants go through photosynthesis, they take in CO2, turn into sugars. We then eat the plants, us being animals and anything else like that, and take in those sugars and then digest it and breathe out CO2. So plants take in CO2 through photosynthesis, and respiration releases CO2. So those are like a give and a take in the carbon cycle. Now, over millions and millions of years, some organisms, particularly like diatoms in the oceans, have been covered with sediment. And they were exposed to a lot of high heat and a lot of high pressure and turned into fossil fuels. Now, we are pulling those fossil fuels out of the ground and burning them, which causes that CO2 or that carbon to be released into the atmosphere. So notice there's no connection here because the CO2 is kind of brand new to the system. It's now being pushed in the atmosphere by fossil fuel burning. So via respiration or via human emissions, carbon dioxide gets into the atmosphere. So the atmosphere is kind of like a sink for a lot of carbon dioxide. Now, depending on the concentration of the carbon dioxide in the atmosphere, it may or may not dissolve in the ocean water depending on the concentration between those two bodies. But a lot of times, carbon dioxide in the atmosphere will diffuse into the oceans. And in the ocean, the CO2 will then cause it to acidify. It can be used by photosynthetic organisms as well, or it can just kind of start to build up there, which is what's happening at the moment. But the same interplay between photosynthesis and respiration also plays out in the ocean. Marine photosynthesis, marine respiration, they also alter and take in or give out this carbon dioxide. So the biotic piece of it is taking in CO2 or breathing it out, pulling it from underneath the ground and using it, which is exporting it into the atmosphere. And the same thing happens in the ocean, except for the fossil fuel burning part. Although the CO2 does make it into the ocean. But at the same time as these biotic processes, abiotic processes are occurring. So you have weathering of rocks that release carbon dioxide. You have volcanic eruptions that release carbon dioxide. Some of that carbon dioxide will be taken in by soil. So soil is actually a big source for sequestering carbon dioxide. So soil will be held underneath the ground, turned into fossilized carbon, or used by microorganisms and through the respiration process and decomposition process, return back to the atmosphere. So you can see carbon dioxide goes between biotic and abiotic, cycles between the atmosphere, the soil, the ground, and the ocean. And it's kind of this big flux between all three of these. Now, the nitrogen cycle, we're going to look at it two different ways. We're going to look at it in a very nuanced way first, and then come back out. And that's because it's really important here for plant growth. So the atmosphere is mostly made up, I think it's about 80% nitrogen. So and it exists in the N2. So atmospheric nitrogen currently exists as N2. That is not usable by plants. And so for it to be usable by plants, it has to go through a variety of ammonification and nitrification processes. So N2 will enter the soil over here, be interacted with a nitrogen-fixing soil bacteria. They will take N2 and convert it to ammonium, NH4. This nitrifying bacteria will then turn it to nitrite, NO2 minus. Nitrite will then also interact with bacteria that turns it into nitrates, NO3 minus, which then can then be used by plants. Some ammonium can be used by plants as well, but nitrates are one of the main pieces for nitrogen for plants. So you can see it's from N2, ammonium, nitrite to nitrate before it can be used by plants is a pretty long process. There's also then bacteria that denitrify it and return it back into N2 into the atmosphere. Now, when we take N2 and we convert it into a usable form in an organism, we call that nitrogen fixing. So it's taking a gas and turning it into a form that's locked inside of something, usually bacteria, plant, or animal, something like that. So it's a pretty long process to get to that. And then decomposers will take the plants and return it back to ammonium, which is a common byproduct of respiration. Now, what's really important here, what's really cool, is that N2 takes a long time to get over here to nitrates. And so in some environments that are nitrogen limited, a lot of plants might struggle. Nitrogen is really, really important for leafy growth, so most plants need it in really high quantities. So if you can't get nitrogen really readily, plants will suffer. But some plants have symbiotic relationships with bacteria. That you can see over here. Here's a legume of some sort of a pea plant. And inside their roots, they have these little nodules that house bacteria in them. And these bacteria, oftentimes rhizobia bacteria, can take convert it into nitrate, and give it straight to the plant. And so rather than going through this whole long process, N2 goes into the bacteria inside the plant's roots and then gives it straight to the plant. In that way, the plants can basically short circuit the system and have a major competitive advantage in a nitrogen limited environment. So in environments that are nitrogen limited, maybe it's a brand new environment, maybe it's one with very little soil development, pea plants are often one of the first plants to colonize those environments. This is also why when you're cover cropping or trying to add a secondary crop to an already ongoing crop, a lot of farmers will choose to add some sort of a pea plant. The reason why is that pea plant not only gives you a secondary crop, but also fertilizes your soil for you. It adds nitrogen to your soil through this process. Now, at a global scale, nitrogen cycle is somewhat similar to the carbon cycle. You have the nitrifying bacteria that we've already talked about. You have an N2 in the N2 in the atmosphere. So this whole little loop is what we've already just talked about. But you also have the addition of fertilizers. So fertilizers will release N2 into the air, but also it'll add to a runoff. So fertilizers will add nitrogen into the water sources around them. And then in the water, there's the same sort of bacteria. So just like if you have a fish tank, you have to cycle your fish tank to start it up. The same nitrifying and denitrifying bacteria also exist in the water. And so you have a mirrored process in the aquatic environment. Although some nitrogen might sediment out into the ocean floor and be fixed there for a while. But basically you have two mirroring nitrogen cycles. This version on land and a similar version over here in the water, often aided by fertilizers. You then also have the phosphorus cycle. Now, the unique thing about the phosphorus cycle is it really doesn't have a major atmospheric component. Like you do have some for volcanic eruptions and stuff, but there's not much in the atmosphere at all. So very little of an atmospheric component to the phosphorus cycle. You have it moving through fertilizers, of course. So NPK, fertilizers, the phosphorus is one of the main components of fertilizer along with nitrogen. I should also point out that this fertilizer leaching in the nitrogen cycle and the phosphorus cycle is because they're anions. They don't bond to those clay particles, and so they leach from the environment really easily. So you add fertilizers, it rains or whatever, you irrigate, whatever it might be, and it leaches out of the environment, out of your field into water bodies. And so those are why nitrogen and phosphorus both highlight fertilizers and leaching as a problem here. So you add fertilizers, it leaches off into the oceans, causes a bunch of algal blooms. It also moves between food webs, gets sedimented out into the ocean, goes through rocks and soil, gets uplifted and dissolved. As you can see, it's mostly moving through either organic food webs, so animals and plants and different things, as ATP and other bodies, or as a abiotic component in rocks, soils, and all the geology. Meaning phosphorus doesn't have an atmospheric component, it just moves between abiotic and biotic environments. Now, both nitrogen and phosphorus in excess, especially from fertilizer leaching, can cause dead zones. So fertilizer can be pretty bad for the environment. When you have fertilizers that contain mostly NPK, like pretty much all of them do, they are anions and they leach from the environment. So when they leach, they're going to leach into the water supply, and they do the exact same thing that they do in the water that they would have done on land. NPK helps plants grow. In an aquatic environment, we have NPK here. Usually N and P are the ones that are leaching out because K is a cation. Oops. So you get excess nutrients leaching into the water here. That causes rapid algae growth. So it fertilizes the water. The algae start to take over really quickly. They start to block out the sun. They grow really rapidly. And as a product of that, they block out so much of the sun, a lot of the stuff down below can't photosynthesize. But also this algae starts to die. So the algae starts to die, things down here can't photosynthesize. And despite it causing a rapid algae production, it ends up actually reducing the amount of oxygen that's in the water. If there's not enough oxygen in the water, animals start to die. And so excess nutrients cause what we call dead zones, big swaths of the ocean usually that have major die-offs every year. A good example of this is actually in the Mississippi watershed, which drains most of the central North America, a lot of the Midwest, all drains through one watershed. So all of the nutrients from all of those plain states drain out through the same watershed, carrying with it an enormous amount of fertilizer. Because of all that fertilizer, it goes out into the Gulf. It fertilizes the Gulf. It causes a massive dead zone and a major die-off. And I will post a video in the supplemental videos part for talking about this. Here's a little map of the dead zones. So you can see we have a couple dead zones off California, one off the North Pacific. Some major ones here up the Gulf, that's due to the Mississippi. So all of this gets drained out to that one watershed. You can see a lot on the East Coast, a lot over here in Europe, and a lot over here by China and Japan and stuff as well. So dead zones are growing. They're an increasingly large problem, and some of them are extremely devastating. We then have the sulfur cycle. So sulfur is a big component in DNA and RNA. And it often comes from, besides agricultural sources, decomposition of organisms, volcanic eruptions, and geothermal vents. So decomposition, volcanic eruptions, and I don't think they have geothermal vents on there, but basically the same idea over here. Also, fuel burning also does release some of this. So hydrogen sulfide will go into the atmosphere. Now, it's also a major component of acid rain. So when you get a lot of salt in the atmosphere, it will create hydrogen sulfide gas, or sulfuric acid, and it'll rain out on top of everything below it. And it can cause a lot of damage to both plants and human structures. Now, on the West Coast, we don't get too much acid rain, but on the East Coast, there's a lot more of it. And it can be a quite devastating process. A similar situation here. So marine ecosystems will have sulfur production. It'll sediment out as well into the soil and move through the environment in a very similar way as the other nutrients. So to recap, nutrient cycles, we talk about carbon, nitrogen, phosphorus, and water in a lot of detail, and a little bit about sulfur as well.